Hello everyone, welcome to the Ulster University's Geotopics 2020 session, and this time we are going to focus on dynamic coasts. My name is Professor Derek Jackson and I am a coastal geomorphologist in the School of Geography and Environmental Sciences. I'm going to try today to give you first of all an overview of the system that actually forces dynamic coasts into the way they behave. Then we're going to move on to how beaches respond to high energy storm events, and then we're going to look at how we as a scientific community look at using different methods to understand the dynamics of these coasts. And then I'm going to wrap up today with looking at local examples which are all too often absent in many of the textbooks that you probably all use. So looking on a global scale, we can see that the Earth is pretty much categorized into pretty high energy wave height zones or regimes, and where we are pretty much getting hit with a lot of high energy events, and then outside of that there are low energy, but in general we would be pretty much well placed in a high energy wave storm events location. When we look at tracking some of these high energy events, we can see that they do resume a pretty established pattern across the Earth's surface. And when we look at where we are, every so often we do get certain track lines of these high energy hurricane events hitting our coastline. Thankfully, not too often, but not impossible. When we look at the global big picture scale, particularly in the Atlantic, we can see that since 1967 until 1991, in a recent research project, they were able to establish that there was a significant increase in wave heights over that time period. And in terms of, on general, where we are, wave heights have increased between 10 to 15% over this 1967 to 1991 period. When we look at what makes up a high energy event, this is, if you like, the ultimate extreme, where we have, in this case, particular event being forced by a hurricane episode. And Hurricane Katrina, which you see imaged here, was one of the biggest events to stem from the Gulf of Mexico. And even though we are a considerable distance away from that, we still feel the effects of that. As the storm dissipates, it leaves behind a signature of wave heights which find themselves traveling across the Atlantic Ocean, and we will ultimately get affected by those events. When we try to pick out which one of these in particular has had a significant impact on our coastline, we can see that in 1961, one of the very few real large-scale hurricanes to actually hit Ireland impacted along the western seaboard of Ireland. It caused huge damage and resulted in loss of life and infrastructural changes as well. And we still see significant impacts and signatures of that event locked up inside particularly dune fields as well. Okay, so let's have a look at when we have a storm occurring, what impact it has on the beach system. So this is showing you a schematic of a cross section of the beach. And as the storm passes, it crosses the coast, atmospheric pressure, wind speed and direction all change. And this gives us high and low energy events pushing across a very focused area of the water-land interface. So we have high and low water levels or surges. We have high waves generated from distant wave events or localized wind-driven waves. And these combine to give what's known as a storm surge. Now, rarely we exceed these values more than 0.5 meters on open coasts, but when we get to enclosed seas, these can feel like funnel themselves into much higher elevations. So they can be quite dangerous events. So effectively what we get from this is coastal flooding, and that extends the upward and the landward limit of the wave action itself. So we get coastal erosion, and this is what most people associate with storms and the coastal response. And so a dynamic coast is something that is clearly visible and reacts to these high energy events. It's important to look at timescales within dynamic coasts, and particularly the importance of low frequency and high magnitude events. So these things are not happening very often, but when they do happen, they are containing a huge amount of energy. And this gives us coasts or coastlines that respond very, very rapidly to these events. So we're looking at timescales and coastal processes and responses. Exceptional storm surge examples. In 1953, we had the North Sea surge. We had massive damage and around 2,400 deaths. It was produced by effectively elevation of water levels during onshore winds and at night time, which made things even worse. And we had storm surge values in excess of 3 meters and up to 5 meters in particular sites. Now, at that time, we didn't have a lot of sea defences. Proper coastal management wasn't in effect. So if you like, this was the perfect storm. And unfortunately, that brings with it huge loss of life and infrastructural damage. Moving more recently, we had Hurricane Katrina. This was so far the costliest hurricane to date in recorded history. And we had about 1,800 deaths in the US alone. Elevated water levels and very strong winds, up to 280 kilometers per hour, brought with that storm surge values between 3 and 8 meters. So when we look at the very fundamentals of how a beach reacts, when we have storm-induced changes, what are the actual effects on a beach? Taking a simple cross-section and a pre-storm on the left-hand diagram, we have a pre-storm profile. So you can see the storm hasn't actually hit yet, and the beach cross-section is quite a low angle, and it contains quite a lot of loose sand material, and vegetation is quite well established at the back of the beach. Once we get a storm, so during a storm on the right hand diagram, we have effectively stripping of sediment from the subaerial beach. We have deposition in the nearshore zone, typically into a formation known as a sandbar. Possible development of a steep erosional scarp can take place depending on the type of material you're dealing with, and that can be on the beach face or on the frontal dune system itself. Beach erosion effectively is clearly visible on these dynamic coasts, and we have what's known as commonly a beach cut, and that may last only a few hours, and it can actually have dramatic effects, particularly if you have infrastructure that's sitting on top of that eroded scarp or just back from it. So we're getting significant displacements of sediment from the subaerial beach to the nearshore sandbar, and that's the natural mechanism of beach protection. So effectively the beach is trying to protect itself. It's taking sand from the beach, it's relocating it to the nearshore zone where the waves are actually starting to really hit the coastline. But occasionally that is not sufficient, and when that becomes no longer sufficient, this is when we get significant erosion. So if beach cut is insufficient to satisfy this demand for nearshore sediment, that would normally reduce incident wave energy and force the wave breaking on the bar. But when that is overridden and no longer sufficient, then we get dune erosion or cliff erosion. And you can see this can be quite dramatic in places, and particularly when you have misplaced or badly planned housing development sitting on these very erosive coastlines, which they should not have built on in the first place anyway. But that's another story. So let's look at some of the really high energy events that outside the Europe, particularly we have Barrier Island systems, And if we have a barrier island system is naturally attuned to these events, by the way. So in Hurricane Ivan on the Alabama coast in 2004, I would like to draw your attention to the first image here, which is before the event took place. Now, as a georeference point, if you like, the red box area is a lighthouse. So I want you to look at that lighthouse and use that as a reference point and use it as a comparison to what has happened after Hurricane Ivan goes through. So this is a fairly stark reminder of the sheer power of these hurricanes, and within just a few days, this is what the aerial reconnaissance captured. Draw your attention to where the lighthouse is and hasn't moved, but effectively where number 1 was is completely gone, and 2, 3, 4 and 5 have been dramatically re-sculpted and re-altered again by this event. Dunes and barriers produce really spectacular records of storm effects, and in Hurricane Katrina we had some pretty impressive before and after shots. Again, the top image is showing what happens when just before the event happens and what the morphology is looking like. After the event is a lower image, and those yellow arrows are reference points of where you can compare changes. When you fly over this with airborne LiDAR, you can see what was like before. On the green, it's showing you the green topography of what those barrier islands were looking like. And after the barrier has been impacted by these events, the red is showing what the end result of redistributing and turning over these barrier islands has looked like. So thankfully, for a scientific point of view, we are blessed with some really nice technology to try and capture this. So what you're looking at on the left hand side here is an airborne LiDAR image of the Dauphin Island, and that is showing you the three-dimensional topography or the heights of the landmass. So the reds and the greens are the higher, and just take a note of the central road strip running up the middle of this. And those reds and greens are actually condominiums. Okay, those are people's properties. So post Ivan, you can see the road has completely been covered or else destroyed by the event, and a lot of properties have simply disappeared. Okay, they've disappeared, they've collapsed into the sea from these events. Then in post Katrina, you can see the same shot of what happens when people still insist on having properties in these types of environments, these dynamic coasts. And you can see that it's pretty much devastation all around. And a point of reference here is the central road running up the middle. And literally from the left hand side, you can see dozens and dozens of houses, whereas there's literally less than a dozen houses in this shot. So pretty powerful dynamic response to high energy storm events. Okay, so let's have a look at what we use scientifically to capture these dynamic coastlines and how they behave, particularly with these before and after events. And this gives us a really good way of quantifying how much material has changed and moved around as a response to these dynamics. And I think everyone knows here that in the last 10 years, we've had a really high increase in the number of drones that are now available. And these are quite a low cost way of capturing what the three-dimensional surface of the coastline looks like. And this is actually one of the drones we have in the department here. And from that, we can extract three-dimensional surface shapes. On the ground, we can mount what's known as a terrestrial laser scanner. So these are tripod mounted, and they fire around about 1 million points or laser points per second, and it gathers the three-dimensional topography that it surrounds it in 360 degrees. We have highly accurate GPS systems, and this is one of our postdoctoral personnel mounting a base station down in Newcastle, County Down, and we're trying to establish a very accurate location device that we then attach on moving vehicles. And then we have GPS mounted survey vehicles, and these are capturing in the vertical accuracy less than a centimeter in terms of its accuracy. So it's a pretty fast, effective way of gathering three-dimensional surface information. Another common way of looking at it on a much bigger scale is repeat satellite imagery or aerial photography, and this is a great way of capturing a large expansive coastline, and if we have repeat images we can look at the changes in these dynamics on these coasts. Scientifically, we also use computer modeling, and on the left hand side we have a static shot, on the right hand side we have a mobile three-dimensional constantly changing wave model. So this models what the waves look like in the near shore and how they approach the coastline and how they change as they enter shallow water. And this is a remarkable way of expanding our reach. We have enough instruments to actually extend right into the sea. So we are able to use very complex three-dimensional modeling. In this case, we use what's known as a SWAN, shallow water wave forecasting model. So I'm going to bring you to some of the local case studies we've looked at. These are some of the sites that are part of ongoing research investigations. Starting off to the southwest, we have Inch Spit in County Kerry, Five Finger Strand in Northwest Ireland, all around the north coast here, and then I'm going to wrap up finally with Dundrum Bay in Newcastle, County Down. Inch Spit is a major dune system, and it has been really scarred by 2 or 3 really large storms in recorded history. Between 1839 and 1999, we had 2 of the highest ever recorded in Ireland. And when we look at this as a single big system, we're trying to look at how that dynamic coast has changed over time. So looking at aerial photography, old maps, we're able to look at shoreline positions and how they've changed throughout time and where these storms have actually impacted and caused massive retreat. You can see the green is, if you like, the most up-to-date in this particular study, 1973. We then looked at 1894, 1949, and how the coastline has changed over time. So this gives us a really long-term view of the coast and what storms may have impacted and changed its shape. So if you look at a time scale on the bottom here and the actual erosion and accretion on the vertical axis here, effectively the system is going through several large-scale changes. In 1839, we had what's known as the Night of the Big Wind, which was one of the biggest hurricanes to actually hit Ireland, and it caused a massive retreat. Around about 100 meters of the coastline retreated in just a few days. Now, over time, we have recovery. So the coastline starts to come back, the sand doesn't miraculously disappear, of course. It's just put into the nearshore zone. Waves over time will bring that sediment back. Wind will blow it up into the back beach area. The dunes will recover and the coastline starts to creep forward again. So then in 1961, we had a similar, if not higher energy event called Hurricane Debbie. And that actually knocked the coast back to the 1839 position after the Night of the Big Wind. And again, the coastline slowly recovers again. So every so often, big events come along and change the coastline dramatically, but the coastline normally will recover again. Moving up to Northwest Ireland, we have Five Finger Strand in County Donegal, and we're looking at this as a high energy system that is responding dynamically to these big storm events. And what you're looking at is an aerial photograph of the site, the dunes on the right hand side, the beach with the red box around it, and those dotted lines are simple profiles that we use to reprofile on a regular basis and see how the system's behaving over time. In 2017, we had Hurricane Ophelia, which turned into Storm Ophelia as it approached the Irish coastline. And that was one of the biggest hurricanes on this part of the Atlantic to form and move north and hit the Irish coastline. And it caused phenomenal damage on certain parts of the coast. And what we're able to do is measure the before and after effects of the storm on this coast. So with wave modelling, we're able to see the red areas here are representing high wave energies. And you can see as the storm is progressing, the energy will move and follow the storm. And up in Malin Head, Northwest Ireland, we are able to see how the storm unfolds and what the waves are looking like over time. Using a terrestrial laser scanner, we can go out before the event, we can go out after the event, and taking the two surfaces away from each other, we can see that the beach changes in different areas, and the reds here effectively are erosion, and the blues are the accretion or the build-up. You can see a simple single beach undergoes dramatic changes, but it's not spatially all the same. So the left-hand side of the diagram here, you see the reds, they're showing the beach has lowered, it's eroded, and a lot of material on the right-hand side has been stripped from the dunes, brought into the central strip, so if you like, effectively it's building up the middle of the beach. So beaches aren't simple erosion build-up. They vary over time and they vary over spatial context as well. Looking at the shoreline positions on Five Finger Strand, since 1952, the coastline has actually undergone significant erosion, around about 100 metres, and that has lasted and consistently is still occurring today. And we believe that it's going through a cycle probably every 50, 60 years, that it's going through erosion, accretion, erosion, accretion. So this is a high energy exposed Atlantic coastline, and we have at the moment exceptional dune retreat occurring. All right, just onto the north coast, we have a whole series of beach systems that we survey on a monthly basis and have been doing so for the last 10 or 15 years. So we're able to look at, with using a GPS, some quad bike work, we can actually occupy profile lines on a regular basis. And using the quad vehicle and the GPS mounted on top, we can effectively take a slice of the beach topographically and repeat that on a monthly basis, year on year. So effectively what we do is take an integral of underneath the beach, and we calculate the area under each profile, and we use that figure as a way of quantifying the volumes of the beach at any one particular month. Just give you some examples. We are occupying I'm going to pluck out just a few. I don't have time to go through all of them, but Portrush West Strand analysis, P2 and P5, for example. We can see that P2 and P5 these are effectively the areas under those curves, under those profiles, and how they change over time. So you can see on the left-hand part of this figure is 2012, then it moves right up to 2014. And over that time, you can see that the beach volume is changing over time. So in this strip here, we have loss, and this is in the winter period of 2013. Again, the beach will build up again, fairly static over this time period, and then erosion again in 2013, 2014. So you can see that in Portrush West Strand, like many of the beaches on the north coast, they undergo erosion, they undergo accretion, and some stability for a while, and so they're dynamically changing all of the time according to the storms that are hitting them. But effectively over this period of time, we can see that the volumes are losing quantities from these profiles over this particular time period. Now, in a single profile, these are monthly profiles put all on the same graph. You can see that there is quite a dramatic change in beach topography even in a month-to-month basis. And we call this the envelope of mobility, and how much vertically those beach changes move through. So this is just giving you a very quick snapshot of between 2013 and 2015, what has happened to the North Coast beaches. Each one of those lines represents Downhill, Castle Rock, Portrush West and East, White Rocks and Port Ballantrae. So just to give you a quick analysis here we have stability over this time period of 2013 up to the winter of 2014. Then we had a lot of storms, back-to-back storms, and the beaches were losing volume. Then that volume that was lost started to come back on again, and the beaches started to restore themselves to the 2013 levels again. Then we had significant storms in 2014, 2015, and some of you may have remembered on the North Coast here, a lot of dune erosion, the beaches were significantly lowered. And after that, the beaches began to recover again. So they go through natural erosion and recovery periods again. And then the final site I'm going to talk about very briefly is Murlock. Now, I don't have a lot of time to give you full details in this, but if you remember or take note of this web link, there is a video and that will show you a lot more detail of what is happening in terms of the project we have ongoing at the minute. The project is known as MARPAN, and we're looking at storm impact on Murlock Bay, where the storms are focusing on, how the changes are taking place. We're looking at historical shorelines, the cross section, these little black lines that are drawn on the image here is showing you the repeat profiles that we undertake on a monthly basis on the site to show us how these beach changes take place, just like on the North Coast. Then we're going to look at the longer term sea level rise implications for the coast. With sea level rise, we will get inundations, we'll get certain areas of the coast that will be vulnerable, particularly the low-lying areas, and we're going to look at the extent of that flooding that might take place. But effectively, this site has undergone historically in the last 50 or 60 years longshore sediment transport. So sand has been losing its volumes from the Newcastle area, and with longshore sediment transport, it's being pushed down towards Ballykilner. Now, what this project is going to look at is how much of that has happened over the years, where it is happening, and how much it's likely to happen in the future. And with these results, we're able to better advise the management on this site. I'm going to finish then with an absolute blatant plug for my recent book that is just out a few days ago. And this is a book that's aimed at largely undergraduates, but geography teachers could learn a lot of information from the various texts. We have 29 chapters here, and it is the largest collection of sandy beach morphodynamics in the world, apparently. So if you want that, you can click on the link below. And that is basically it. And hopefully you've enjoyed this little session. And I know I've rushed through a lot of this, but feel free to ask me any questions via email or in any other medium. Thank you very much.